All right, let's recall the population growth model that we've been working with this semester so far. So that was the rate of change of population with respect to time is proportional to the current value of the population, with k being our constant of proportionality, and k of course was positive for population growth. There's a problem with this though. It's a pretty low resolution model. It describes the short term, but not really the long term. It ignores things like competition, carrying capacity, what if part of the population is being harvested at a regular basis, or hunted, or whatnot. And none of that's being factored in here. This is just pure growth, right? In fact, we solved this differential equation, and we got that particular function there, which we know doesn't have any really interesting features. It's just exponential growth. Okay, so what we're going to do here is enhance our population growth model to incorporate a little bit more information. So what we're going to do is we're going to consider a related model here. So rather than being numerically proportional to population, we're going to multiply by a function itself dependent on p. So the idea here is that for instance, large population, you might have a small f of p value, and therefore the constant of proportionality, which is no longer constant, would be small when the population is large. So a large population might not be growing as much because there's more competition, more starvation, or whatnot. And when p is a small number, so a low population, then f of p would represent, say, a larger figure, meaning that a smaller population might grow very quickly, representing the idea that a smaller population doesn't have any competition. So what we're leading toward is something called the logistic equation. So let's suppose an environment is capable of sustaining no more than k individuals. Now this is a capital K in contrast to the little k that was used for our constant of proportionality. This k here is called the carrying capacity. So in our updated model here, what would we want? Well, we would want f of k to equal 0, which means when the population is exactly equal to k, we would want that f of p, or f of k in this case, to be 0, which means that the rate of growth would be 0. So that's right on the line. So that's the environment having exactly k individuals. There would be no more growth. All right. What about the other extreme? What if there's 0 population? What do we want f of 0 to end up being? Well, this will be the equivalent of the old constant of proportionality. So we could call it little k to align perfectly with the old constant of proportionality. However, in this context, it's standard to use a lowercase r. So all we need for f is it to be a function that satisfies those two conditions. Well, you could pretty much make any function satisfy a couple of points, but the simplest thing to do is to let f just be a linear function that goes through those 2 points. So the form of a linear function is, of course, well, mx plus b, right? But we'll call it mp plus r. And we can see right away that f of 0 will equal r. So we've satisfied that first condition. We just need to choose our m, which is a slope here, such that f of k is equal to 0. Okay, but our m is simply going to be the difference in the output values divided by the difference in the input values. Again, from algebra, you saw it looking like this. So our output values will be, say, r minus 0 divided by 0 minus k. So we get negative r over k. Again, this is a capital K. I should be very clear on that. So therefore, our f of p is, I'll write it as r minus r over capital K times p. And therefore, the model here is dp dt, which would be p times f of p, but f of p is r minus r over capital K times p. And again, I will just remind you that K is the carrying capacity. So you can convince yourself of a few things here. One is that if the population is equal to K, this entire factor calculates to 0 because you get r minus r. And therefore the growth rate is 0. So that's the population equaling the carrying capacity. If the population is, of course, exactly equal to 0, you'll also have a growth rate of 0 because there's no organisms. And when p is a very small number, then this term here is insignificant, and this basically behaves like the regular growth rate model that we use, with r playing the role of the little k from the old model. Now this is a pretty flexible concept here, so we're actually going to relabel the constants to give even a more general logistic model that applies to more than just population growth. So instead of using r and k, we're going to use a little a and a little b. And here, our a was simply r, and our b is what used to be r over k. And this here is called the logistic equation. You can see that it's an autonomous differential equation. So two solutions immediately come to mind are p equals 0 and p equal a over b. The logistic equation is separable, so we can solve it. So let's solve it. Notice it's not linear, which is why this is not a 3.1 example. It's a 3.2. It's nonlinear. So let's paste it in here. This is where we left off. And let's separate the variables. So we have something like this. And we can now integrate both sides. Okay, well, obviously the left side is the interesting side. The correct approach is to use partial fraction decomposition. Now I'm going to omit all the side work for working out the partial fraction decomposition form and just jump straight to what the integral turns into. So we get 1 over a, and that's all divided by p, plus b over a, and that's all divided by a minus b times p. And the right-hand side, of course, is the integral of dt, which would be t plus some constant. And integrating this, we get 1 over a times ln of absolute value of p plus b over a times negative 1 over b ln of absolute value of a minus bp. So there was a quick little u substitution, which gave us the negative 1 over b that came out. And this is equal to t plus our constant, c1. All right, let's clean up the left here, and we actually can isolate p. So first let's multiply everything by a. So we get ln of absolute p minus ln of absolute a minus bp, because those b's canceled, is equal to at plus c2. A is just a constant here. We can combine these logs. And we'll exponentiate both sides. Well, we've been down roads that look like this before many times. And we can burden the right-hand side with plus or minus. So let's go do that. But let's also just allow C4 to equal 0, because we know that P equals 0 is a solution. All right, to isolate P, we need to bring the denominator over to the other side. So we have P is equal to A minus BP times C4 times e to the AT. And we'll have to distribute on the right-hand side and then bring that p back over and factor it. So we'll have p is equal to a c4 e to the at minus bp c4 e to the at. All right, bringing all the terms with p together, we have p plus bp c4 e to the at is equal to a c4 e to the at. So we can now finally factor p on the left, and we're almost done getting it isolated. And dividing everything by that 1 plus stuff, we get this. Okay, well, let's consider that C4 to be our last constant, so let's just call it C. And it's also a little bit more convenient if we multiply everything by e to the negative at, so we get AC over BC plus e to the negative AT. All right, so we are missing the singular solution that we determined at the very early stage, which is P equaling A over B. And you can actually see that that's an asymptotically stable critical solution, because if you let t approach infinity, then you simply get P is equal to A over B. However, there's no constant we can choose for C that would generate that solution, which is why we have to independently write it in. Okay, let's take a quick look at this thing on Desmos. For Desmos, it's best to use y in terms of x. We could probably use y in terms of t here. But I don't think it'll be happy if we use a p. So we'll go a times c divided by b times c plus, it doesn't really like the, let's put an x in there. Didn't like the t. All right, so this is the curve we're getting. So let's see how the different sliders influence things. Remember, the solution a over b, that's our carrying capacity. So a large value of a with a small value of b is going to increase our carrying capacity. So right now we have a carrying capacity of 3 divided by 0.5, which is 6. And you can see that, yeah, as our population gets closer to 6, remember the c value is generated by the integral. It's the parameter generated by the fact that this is a first order differential equation. And you determine the c value from some initial conditions. So the c value simply depends on the initial population. Right here we have a c value of 1, It doesn't mean there's an initial population of 1, because according to our graph, the initial population is 2. At time 0, we have 2 individuals. However, we can slide the C around and change that initial population. And in fact, if you get a little extreme here, at C equals 0, that corresponds probably to an initial population of 0, which is why for all time the population is just fixed at the constant 0. All right, let's get a better look at our C value. It's a little unsatisfying to have all these A's and B's and C's in here. So we know that we usually have an initial condition. So if we're told that P of 0 is P0, then we can determine C in terms of P0. So let's look at our solution here, and we'll go replace P with P0 and T with 0. Okay, so what we have is P0 is equal to AC over BC plus 1. So let's just solve this equation for C. All right, so let's distribute. We have BC times P0 plus P0 is equal to AC. Let's move all the terms with a C in them to one side. So how about we go P0 is equal to AC minus BC times P0. And we can factor C out of the right-hand side. And solving for C, we get that it's P0 divided by A minus BP0. All right. So then our differential equation, which was this, becomes A times this creature here. Oh, this is looking lovely. Okay, well, it's not so bad because we can just multiply the top and bottom by A minus B P0, and we get A P0 over B P0 plus A minus B P0 e to the negative AT. And so this is the solution to the logistic model subject to the initial condition P of 0 is equal to P0. Okay, very exciting. So, well, let's see this in an example. All right, let's revisit a problem from section 1.3 that was actually on your homework. So we have the student returning to a campus where there is a population of 1,000 students. And the student has the flu, and we want to determine a differential equation tracking the number of students who have contracted the flu. And it's jointly proportional to the number of students who have the flu and the number of students who have not yet been exposed to it. So let's assume that the student coming in is the only one with the flu at the start. But we don't need that to actually establish the differential equation, but we do for the initial value. Of course, in your homework, you were only asked to come up with the actual differential equation as it's written here. And you obtained this as your differential equation. dx dt is equal to k times x times 1,000 minus x. Here, where x is the number of students who have contracted the flu. All right, and that was the end of it as a 1.3 problem because we didn't know how to solve differential equations. Well, now of course we do. So let's solve this differential equation. And let's even impose the initial value that at time 0, we have one person with the flu out of the 1,000. So that's the person who came back with the flu. With not too much difficulty, you could probably just solve this differential equation from scratch. It's not linear, but it is separable. So you could just divide by this thing and then use partial fraction decomposition and you're going to get a solution. However, the work involved would be commensurate with everything we did earlier to solve the logistic equation. And I'm personally a fan of reusing information that continues to be relevant. So let's just compare this with the generic logistic form that we have and see what our A and our B values are for this specific situation. So what we have is the generic logistic equation with P replaced by X would be this thing. Okay, so we can see that in this situation, A here is equal to 1000K, and B is simply equal to K. So therefore, we can jump straight to the solution, X of T, which we know is A times P initial divided by B times P initial plus A minus B P initial e to the negative AT. So this is like the generic version. And let's put in all of our pieces because we know, let's also write it over here. P initial, of course, is 1 because there's one person who's sick at the start. So our A is 1000K, so we have 1000K times 1. Our B is simply K, so we have K times 1 plus A, which is 1000K minus K times 1 e to the negative A, 1000K times T. So this is, this cleans up a little bit further. We can divide everything by K. All right, so this would be the solution to that particular initial value problem. So we still have an unknown parameter, which is K, and we would need more information from the situation in order to determine K. Look at the model, by the way, and convince yourself that at t equal to 0, our x value is simply 1. Because when t is equal to 0, then we just have e to the 0, which is 1. So we got 1,000 over 1 plus 999. So that's the whole thing equals 1. And also convince yourself that this term is transient. So when t increases to a very large number or approaches infinity, then x approaches 1,000. All right, let's add some more information in that will help us determine the value of k, and our model will be very specific at this point. So let's say that 7 days into the experiment, or 7 days into everybody being back at campus, 50 people have the virus. Well, we can use that to determine the value of k. So what this is saying is, of course, x of 7 is equal to 50. So we have 50 is equal to 1,000 divided by 1 plus 999 e to the negative 1,000 times k times 7. So we're just going to solve this for k. Okay? We'll bring the denominator all the way over, so we have 50 times 1 plus 999 e to the negative 7,000 k. That's equal to 1,000. All right, we can certainly divide everything by 50 and get 20 on the right-hand side. Okay, and try to keep up with this next step here. And now we'll divide by 999. Okay, we're almost done. We're just going to log everything. So, isolating k, we get k is negative 1 over 7,000 times natural log of 19 over 999. Okay, super cool. So let's go back to our model and update it with our k value. And there'll be no more constants in it, right? So we have x of t being 1,000 divided by 1 plus 999, e raised to the negative 1,000 times k, which is this, times t. Surely that cleans up a little bit. Let's see. Looks like we can just say that that's t over 7 times ln of 19 over 999. And in fact, we can write that using a base of 19 over 999. So this is 1 plus 999 times 19 over 999 to the t over 7. All right, that's a pretty nice looking answer. Okay, let's convince ourselves that at t equaling 0, we still have one person. So I'm convinced when t is 0, this whole exponent part just becomes 1, so you get 1,000 over 1,000. That's 1, good. Let's convince ourselves that when t is very, very large, we get 1,000 people who are sick. And I'm convinced that as the limit as t approaches infinity, this base here being less than 1 means that this entire exponential factor goes to 0. So we end up with 1,000 over 1, which is 1,000. And let's convince ourselves that the initial condition is satisfied, that when t is equal to 7, we have 50 people with the virus. So at t equal to 7, then we have exactly one copy of the base here, 19 over 999. The 999s cancel, and you get 1,000 divided by 1 plus 19. So that's 1,000 over 20, which is 50. So everything is super awesome, especially if you got the flu shot, as I did this morning on the day that this lecture is being recorded by coincidence. Okay, so now we can answer a question like, when will 500 people have the virus? So this is a question where we solve for t. So we have 500 equals 1,000 divided by 1 plus 999, 19 over 999 to the t over 7. And we're going to solve for t. Okay, well, certainly we can immediately divide everything by 500, and we get a 1 here and a 2 there. So by moving that whole big fat denominator over to the left, we get 1 plus 999 is equal to 2. Okay, let's subtract 1 from both sides. Did I really just write that? And divide everything by 999. Okay, so now we're going to take the log of both sides and we're going to bring down the t over 7. So we get t over 7 times ln of 19 over 999 is equal to the log of the right-hand side, which is probably cleaner if we just write it like that. And now we'll divide everything by the logarithm of 19 over 999. So we have t over 7 is equal to this thing. And of course, we'll get our t value here. So t is equal to negative 7 ln of 999 over ln of all that. You can even write it as like ln of 19 minus ln of 999 if you want. And in fact, we can clean that up a tiny bit. There's a whole bunch of ways that you can write expressions that have a bunch of logs in them, as you know. That way looks pretty cool. On a calculator, I get that this is approximately 12.2. So 12.2 days into the experiment, 500 people will have the virus. All right, let's feel victorious and look at this on Desmos. Again, we should call our dependent variable y for Desmos and our independent variable x. So instead of x being a function of t, we'll write this as y a function of x. So what we had was 1,000 divided by 1 plus 999 times 19 over 999, close parentheses, raised to the t over 7. But we'll have to go x over 7 here. Look, we have what appears to be exponential growth. That's actually pretty awesome. Okay, so here's our graph. You can see it's totally got the shape of a logistic curve. And once we get close to 1,000, we're going to be asymptotically close to 1,000. Of course, in real life, you don't have partial people with partial flu, so you're just going to have, you're probably just going to hit 1,000 and then everybody's got it. So we decided a few things. We know that on day 0, 1 person has it. We saw that on day 7, 50 people would have it. So let's go see if that's true. It's not snapping, but there we are, 7, 50. And we projected that on day 12.2, there would be 500. So let's go, it's probably easier just to go up to the 500. And see if, yeah, look at that. It's not snapping, of course, because the definition of that 12.2 was a whole bunch of logarithms. But we nailed it, of course, because we can do math. All right, well, that was fun.